explorations in the computational universe, I came up with a hypothesis that I call the principle of computational equivalence. So let me explain it a bit. When we have a system like Rule 30, or like the system here, like something in nature, we can think of it as doing a computation. In effect, we feed in some input at the beginning, then it grinds around, and eventually out comes some output. Then the question is, how sophisticated is that computation? Well, we might have thought that as we make the underlying rules for a system more complicated, the computations it ends up doing would somehow be progressively more sophisticated. But here's the big claim of the principle of computational equivalence, that that isn't true. Instead, after one passes a pretty low threshold, and one has a system that isn't obviously simple in its behavior, one immediately ends up with a system that's doing a computation that's as sophisticated as anything. So what that means is that all these different systems, whether it's Rule 30 or whether it's a fancy computer or a brain, they're all effectively just doing computations that have the same level of sophistication. Well, okay, so there's an immediate prediction then from the principle of computational equivalence. There's this idea of universal computation. It's really the idea that launched the whole computer revolution due to Alan Turing and friends. You might have thought that any time you want to do a different kind of computation, you need a different system, completely different system. But the point of universal computation is that you can have a single universal machine that can be programmed to do any kind of computation. And that's what makes software possible, and that's the foundation for essentially all computer technology today. But okay, the principle of computational equivalence has many implications, but one of them relates to universal computation. It says that not only is it possible to construct a universal computer, but actually it's easy. In fact, pretty much any system whose behavior isn't obviously simple will manage to do universal computation. Well, one can test that. Just look, for example, at these simple programs like Rule 30 and see if they're universal. We don't yet know about Rule 30 in particular, but we do know, for example, that a program very much like it, Rule 110, is universal. A few years ago, we found that even among Turing machines, the very simplest one that shows not obviously simple behavior, though it still has a very simple rule, is also universal. Now, we might have thought that to build something as sophisticated as a universal computer, we'd have to build up all kinds of stuff. We'd, in effect, have to have this whole civilization that figures out all of these different kinds of things. But actually, what the principle of computational equivalence says, and what we found out is true, is that actually out there in the computational universe, it's really easy to find universal computation. It's not a rare and special thing. It's ubiquitous. And for example, it'd be easy to mine from the computational universe, say for the particular case of practical importance of making molecular computers or something. Well, okay, the principle of computational equivalence has other implications too that are pretty important. One of them is what I call computational irreducibility. See, a big idea of traditional exact science is that the systems we see in nature are computationally reducible. We look at those systems, say an idealized Earth orbiting an idealized sun, and we can, with sort of all our mathematical and calculational prowess, we can immediately predict what those systems are going to do. We don't have to trace every orbit, say. We can just plug a number into a formula and immediately get a result, using the fact that the system itself is computationally reducible. Well, it turns out that in the computational universe, one finds that lots of systems aren't computationally reducible. Instead, they're irreducible. There's no way to work out what they will do in any reduced way. There's no choice but just to trace each step and see what happens. It's actually pretty easy to see why this has to happen, given the principle of computational equivalence. We've always had kind of an idealization in science that systems we study are somehow computationally much simpler than us as observers that study them. But now the principle of computational equivalence says that that isn't true, because it says that a little system like Rule 30 can be just as computationally sophisticated as us with our brains and computers and so on. And that's why it's computationally irreducible, and by the way, also why its behavior seems to us so complex. Well, computational irreducibility has all sorts of implications for the limits of science and knowledge. At a practical level, it makes it clear how important simulation is and how important it is to have sort of the simplest possible models for things. And for example, a philosophical level, I think it finally gives us an explanation for how there can be both free will and determinism. Things are determined, but to figure them out requires an irreducibly large computation. But okay, so the principle of computational equivalence has another implication that relates to intelligence. There are various concepts, like life, for example, that always seem a bit elusive. I mean, it's pretty easy to tell what's alive and what's not here on Earth. But all life shares a common history here and has all sorts of detailed features in common, like cell membranes and RNA and so on. But what's the abstract definition of life? Well, there are various candidates, but realistically they all fail. And either we have to fall back on the shared history definition, or we have to just say, in effect, that what we need is a certain degree of computational sophistication. Same thing with intelligence. We sort of know historically what human-like intelligence is about, and we don't have a clear abstract definition sort of independent of that history, and I think ultimately there just isn't one. In fact, it's sort of a consequence of the principle of computational equivalence that we can't make one, and that all sorts of systems are ultimately equivalent in this way. I mean, there are expressions like, the weather has a mind of its own, and one might have thought that that was just some very primitive, animistic point of view of the world. But what the principle of computational equivalence suggests is that, in fact, there is a fundamental equivalence between what's going on in, for example, the fluid turbulence in the atmosphere and things like the pattern of neuron firings in our brains. And this